This video is on the second part of Chapter 5. It's going to look at situations where we have two genes that affect the same phenotype. So we've looked at a couple of examples of two genes at one time in the past. We started out by looking at Mendels' work with dihybrid crosses. These would be unlinked genes. And then we moved to looking at genes that are linked. We're going to go back to looking at two different genes that are unlinked, so similar to what Mendel did, but it's going to be slightly different in that those two genes affect the very same trait. So I want to just review what we found with Mendel. So if you cross two true breeding lines, you would get a dihybrid individual. And this is a dihybrid individual with two different traits. So they both affect the P itself, but they're really two distinct characteristics. One affects the color, green versus yellow, whereas the other affects whether it's wrinkled or round. So these are independently assorting genes, and Mendel did a self-cross to get an F2 generation in which you get this 9:3 to 3:1 ratio. We're going to be looking at situations that are very similar to this, looking at those very same ratios. So we're going to have to be really comfortable with what these are. I want to just remind you, when you have this 9:3 to 3:1 ratio, it's always the double dominant phenotype that is the 9 class, and the 2-3 classes have one dominant phenotype and one recessive phenotype, and then the 1 class has the double recessive. The way I like to focus on this material is by looking at pathways. So this is a biochemical pathway that's found in humans, and this was partially discovered by this physician way back in 1909. Archibald Garrod published this very famous book called Inborn Errors of Metabolism. And in it, he identified some of the first recessive human genetic disorders. He found a bunch of things, and we've heard of some of these before: PKU, albinism. This is all to do with how dietary protein is broken down in our bodies. The really important thing I'd like to highlight here is that the arrows between the different compounds are the place where particular gene products function. So for example, down here is a step converting homogentisic acid into this other acid. And the thing that does that is an enzyme. That's a protein that is encoded by a gene. The name of that gene and that protein are called HA oxidase. Okay, so if you have a functioning copy of that gene, it will encode that enzyme that will catalyze this reaction. If you do not have a functioning HA oxidase gene in your genome, you will not be able to do this step. So Garrod actually identified individuals who did not have any HA oxidase in their genome. These individuals had a condition that he called alkaptonuria, which is also known as black urine. And so what happens here is that homogentisic acid builds up, and that makes individuals' urine actually turn black. So I'd just like to get you thinking a little bit about pathways by thinking about cat eye color. So here are 3 common cat eye colors: yellow, blue, and green. And eye color is a pigment. What we're going to assume is that the genes that regulate eye color encode enzymes that change different precursors into different colored pigments. You may be able to think of a couple of different possibilities of ways that you could produce these different kinds of pigments. One possible way would involve the production of 2 separate pigments in 2 separate pathways. And so what I've written here is simply some precursor pigment being converted by a particular enzyme, enzyme A, into a yellow pigment. And a separate pathway would be a precursor being converted into a blue pigment by a different enzyme. Now, if you get both the yellow and the blue pigments being formed, we know yellow and blue together make a different color. They make green. And so this could be one possible way you could get those 3 eye colors with 2 different genes. I just want to point out what would happen if you have a problem with enzyme A. Just say you have a mutation in your genome that you can't produce enzyme A. This step would be blocked and you wouldn't be able to make yellow pigment. And so the result would be that you still made the blue pigment and therefore you had blue eyes. Likewise, if you blocked this step, making the blue pigment, you would only have yellow being produced and you would end up with yellow eyes. Another possible pathway to regulate eye color would be a linear pathway. So possibly there's a yellow pigment that is converted into a blue pigment by a particular enzyme, and then that blue pigment might be converted into a green pigment by a second gene. So what I want to point out is that if you have a mutation in enzyme A, you actually aren't going to be able to see what is going on with enzyme B. You won't know whether you have this possibility to convert blue pigment into green pigment if you're stuck over here at yellow. So we're going to look at examples of both of these. The first possibility that we talked about here would be two parallel pathways. Again, these are genes that both function to regulate the very same trait. We're also going to look at examples of linear pathways like this second example here. I'd just like to introduce a term that you may not have heard before, and that is epistasis. And so epistasis is particular cases where you can have a mutation in one gene that actually affects whether you can observe the normal phenotype of an allele of a different gene. Okay, first one more example of a parallel pathway. This is actually an example with corn snakes. The wild type has this what's called camouflaged color, and there are actually two things that contribute to that pattern. And if you have a big B gene, you actually get the black pigment produced. And if you have a big O gene, you actually get the orange pigment produced. And these are two separate components that if you make both of them, you end up with the wild type camouflaged appearance. So here are the different mutant conditions. So if you have little b, that would block the production of the black pigment. You would be left with only the orange pigment and you would have this orange phenotype. If you had a mutation in the O gene, you would block this particular synthetic step. You can't make orange pigment anymore, and you would still be left with black pigment and you would get this black phenotype. It turns out that if you have a mutation in both of these pathways, you would end up with no pigment at all, and you actually get albino in that case. So if we look at a dihybrid cross, you're going to get the 9:3 to 3:1 ratio that we observed before with Mendel. Remember, the 9 is the double dominant, the 2 3s are one dominant, one recessive, and the 1 is the double recessive. One characteristic of parallel pathways like this example is that you usually observe 4 different phenotypes. Specifically, the double mutant phenotype is usually different from individual mutants of either of the two genes. So for this kind of example, I expect you to be able to do problems where you predict the results of a dihybrid cross and predict the different phenotype classes and what ratios you expect. I also expect you to be able to write out those parallel pathways and assign gene alleles to particular arrows. I also expect you to be able to interpret those pathways to explain how a particular trait is regulated. Okay, next we're going to talk about linear pathways. And again, two genes affecting the same trait. And here is where we can have an allele of one gene that affects different genes' phenotypic expression. The name of this is epistasis. What we're going to look at here is specific examples where epistasis can modify these 9:3 to 3:1 ratios, and certain phenotype classes would be grouped together in different ways. There are a number of different types of epistasis. We're only going to talk about 3 specific types. So the first type of epistasis I'm going to talk about is recessive epistasis. We'll come back to why it's called recessive epistasis. This example involves Labrador retrievers, and there are 2 different genes that affect the coat color of labs. So the first gene is the B gene, and if you have at least one big B, you're going to be black. If you have little b, you're going to be brown. Now, there's a second gene that determines whether the pigment can actually be deposited onto the hair. And this particular gene is the E gene. If you are dominant for the E gene, either big E or big E little e, you do get pigment being deposited. And in that case, you would actually be able to see what was going on with the B gene. If you have little e, you do not deposit the pigment, so you can't actually tell if you are big B or little b. So if you did a dihybrid cross of these individuals, the progeny would be shown here. And what I'd like you to do, pause the video and think about what would be the phenotype of each of these classes. Okay, so hopefully you got these answers. So as long as you have little e, you cannot make the pigment. So both of these classes that have little e are going to be white coat color. If you have big B and big E, you're going to be black, and if you have little b with big E, you'd be brown. This is a 9 to 3 to 3 to 1 ratio, and we can actually predict that those two white groups are going to join together to make a final ratio of 9 black to 4 white and 3 brown. The next thing I'd like to talk about is how we would write a pathway for how coat color is determined. So in order to do this, I'd like to actually just walk through two different possibilities. It's a little bit tricky at first to figure out what might be a possible pathway, but it turns out that one of these pathways is correct and the other one cannot be correct. Okay, so I wrote these 4 phenotype classes at the top here, the ones that we decided on in the previous slide. We're going to have to come back to this at several times. So we talked about 2 genes that affect coat color. If you have big B, it's going to be black. So I would say that big B catalyzes this reaction. In contrast, if you have little b, that would block that particular step and you would stay at brown. Likewise, we talked about if you have little e, then you would be white. And so we're going to put little e up here as the thing that lets this go through to white. And we're going to put big E as the thing that blocks this particular step. That little T sign is a sign that it's blocking that particular step. Okay, so this is one possible pathway, and in order to test whether this actually works, what we're going to do is then go and look and see, do each of these predict the right phenotype? So if you have dominant for both, we predicted that it would be black, and in fact, if you have dominant for both, you start at the left. You do go through to black with big B, but you get stuck here at black and you can't go through to white. So that one is in agreement with the first item here. Second one, we expect it to be white if you have big B and little e. So big B lets it go through to black, and then little e lets it go through to white. And so this one is in agreement also. The third one, little b, and big E should make brown. And sure enough, you start at the left here and you encounter little b, it blocks that step and you're stuck at brown. The last one, if you're homozygous recessive for both, we expected that that would be white. However, we start at the left here and the first thing we encounter is little b that's going to block that first step and keep it at brown, and we do not ever get to white. So what that tells us is that this pathway is incorrect. It does not work. It does not predict the correct phenotype for this bottom phenotype class. Okay, so that doesn't work. Let's try the next one. So on this one, the thing that keeps it white, we're going to put little e is the thing that blocks that arrow, and big E is the thing that lets it go through. And then big B is the thing that lets it go through to black, and little b is the allele that would block it. Let's see if this works now. If you have dominant for both, we expect it to be black. You start out here, white, goes through to brown, goes through to black. That first one works. The second one is big B and little e, and we predicted that that would be white. And sure enough, we block it here at the very first step. With little e, we can't go through to brown and we're stuck at white. The third one is little b, big E. And so big E lets it go through to brown. And little b blocks the second step and you're stuck at brown. So that one is in agreement. And then finally, the double recessive, we expect it to be white. And so you start at the left here, and the first thing you encounter is the little e, and that blocks that first step, and you're stuck at white. So this particular pathway does in fact work, and it predicts the behavior of those genes on regulating the different co-colors. One thing I'd like to give you a little hint on. The hardest thing to figure out here is which phenotype goes first in the pathway. And in all cases that we're looking at, if you have a phenotype that shows up more than once, so for example, white shows up twice here. This is a combined class because now it made a 9:4:3 ratio, right? We combined these two together. You're always going to put that phenotype first in the pathway, and that's going to be a little hint that's going to help you figure out the correct order. Okay, so here is the pathway that works, and the last thing I'd like to say is that for every problem like this, we can come up with an epistasis statement. So remember, the definition of epistasis is simply that an allele of one gene masks the normal phenotypic expression of an allele or alleles of a different gene. So when we have a pathway like this, it's really easy to see that when we have an allele that blocks the very first step, that is the one that is going to be epistatic to the other alleles. So little e is the allele that is blocking the normal phenotypic expression of both big B and little b. You can't see brown and you can't see black as long as you are little e, little e. Lastly, we call this recessive epistasis because the allele that is doing the epistasis, which is little e, is actually a recessive allele. All right, I'd like to very quickly go through the two other types of epistasis. So the first one is duplicate recessive epistasis. Here an example is campanula flowers. So purple is the wild type, white is the mutant, and there are two genes that are required for the purple color. So mutation in either the A gene or in the B gene would lead to white flowers. And so when you actually have the progeny of a dihybrid cross, here are the phenotypic classes, the 9:3:3:1, and any class that has a homozygous recessive allele is actually going to be white. So this modified ratio is actually 9 purple to 7 white. We add up the 3 plus 3 plus 1. So next, I'd like you to try to write a genetic pathway for this example, and just pause the video. We'll go over it in a minute. Okay, so as we previously discussed, the phenotype with the combined classes, so there were 3 of them that were white, that should always go first. Now, sometimes people write a pathway, for example, white to purple, so it has 2 different arrows, and I prefer not to do that. I prefer to write one big arrow, and the reason is because you don't really know which order those A and B genes function in. We don't have any intermediate phenotype so that we can know the precise order. So if you're dominant for both, you go through to purple. If you are mutant for either A or B, or for both of them, you stay at white. The epistasis statement for this pathway actually has 2 possibilities. Remember that epistasis is a relationship between alleles of 2 different genes. So what we would say is that little a is epistatic to big B, so the normal phenotype of big B would be purple, and if you have little a, it masks the normal purple phenotype. Likewise, little b would be epistatic to big A. We call this duplicate recessive epistasis because both of the alleles that are doing the epistasis are recessive alleles. For the last example, it's going to be dominant epistasis. This example is patty pan squash. So it comes in 3 colors and it's regulated by 2 genes. So if you have a dominant allele W, the squash are going to be white, and it doesn't matter what the Y gene is doing, the second gene. In contrast, if you are little w, then you can actually see the effects of the Y gene. And if you're big Y, or big Y, you would be yellow. And if you are little y, you'd be green. So the way this is going to look, I'm going to write out the results of a dihybrid cross, 9:3:3:1. As long as you have big W, you're going to be white. So those two are going to be combined together. If you have little w, then the Y gene shows its phenotype, and so big Y would be yellow and little y would be green. That modified ratio is going to be 12 to 3 to 1, where the white is the combined class. So what I'd like you all to do is try to write your own genetic pathway, putting the different alleles for the W and the Y gene on that pathway and including all three phenotypes. I want you to write which alleles are epistatic to which and tell me why it's called dominant epistasis, and we will discuss this in class. Last thing I'd just like to show you is that the types of epistasis we talked about are not all of the possibilities. So these are the three that we talked about right in here. There's three more that are also observed.